Hello everyone, and today we're going to be talking about this thing called LQR, which stands for the Linear Quadratic Regulator. So in the last lecture we talked about PID and how PID is pretty useful when it comes to controls so that we can use that measurement from the system to change our controls. So what LQR does is take that to the next. So let's review some dynamics. So remember we can have linear dynamics that are written like this, where we have some matrix A and some matrix B, so we have AX times BU, and we can also have some nonlinear dynamics like this. A lot of control focuses on linear systems. There's lots of nice algorithms that you can use in linear systems. There's nice theorems you can prove. But unfortunately, a lot of robots and a lot of the practical applications of controls end up in nonlinear systems. Now, for LQR, we're just going to be focusing on linear systems. So we're also going to review some optimization things. So remember we had the difference between convex and non-convex. The way to recognize a convex function is any local minimum is also a global minimum. So you can see here in this quadratic function, the only minimum you have is this point right here. There are not multiple minimums like you have in this non-convex function. So if we can find a local minimum, we know that it is a global minimum since we have a convex function. So one really important thing to point out is that quadratic forms like this, so this is going to be some cost function we're going to talk about later, but this is quadratic in x and u. This is a convex function that we can use in optimization. We're going to use this fact with LQR. So to start off, we're going to talk about this thing called optimal control. So I do a lot of my own research in optimal control, and essentially the idea of optimal control is to formulate the controls problem as an optimization problem, and then solve it. So this is the general form of that cost function. So we're going to find the control u that minimizes our cost function. And our cost function is defined with two main components. So we have some phi, which represents a terminal cost, so our cost at our final position. We have some L, which is called a running cost, and it's based on our current location. So the way to think about this is if I have some state trajectory moving along like this, the cost of this trajectory from x0 to xt is just I take my running cost here, take my running cost here, take my running cost there, there, and there, and I sum these, and then add that to this terminal cost here. And we're going to do this subject to some dynamics, which we're going to define as linear. So what is the set of controls that give me the lowest cost defined by these two functions? And this will be defined as a quadratic function, and this will be defined as a quadratic function. So we know that the combination of the two, since each one is convex, is also convex. We can find the best control. So here we're going to set up the linear quadratic problem. So we have some LXU, which is our running cost. We'll define it as a quadratic function. Then we'll have some terminal cost, capital phi. So phi is equal to another quadratic cost, subject to some dynamics, which are linear. So this is the linear, because we have linear dynamics, quadratic, because these two are quadratic, problem, because we're trying to find the control that will minimize this cost function, subject to these linear dynamics. The next thing we're talking about is this thing called a value function. So this is really nice. We can calculate the cost of any trajectory. The value function defines the optimal cost to go starting at some x at some time t. So given some x at some time t, what we're going to do is find the cost based on taking the optimal action at each location. So this is how much cost we have left to go at any given point. So the important thing to remember about this cost to go function j is that it gives you an optimal cost for an arbitrary starting state at time t. So this is based on some time t, and we're going from t to capital T, our horizon. So here I have an integral because we're talking about a continuous time derivation of LQR. Now everything else I'm going to show you and everything else we're going to talk about is going to be in discrete time, so we're going to have a summation. But I just wanted to throw this in there that in case you look at a paper and you see an integral, or if the dynamics are defined in continuous time, i.e. you'll get an equation for x dot rather than x of t plus 1 given x of t. We just flip between sums and integrals depending on if you're in discrete or continuous time. This is nothing to worry about. So what this graphic down here is showing is that it's based on our x. This is parameterized based on x, so it's given a state, I give you a cost to go. So you can evaluate this j at this point, or this point, or this point, or this point, or this point. And what this should give you is what is the optimal cost to go from this point on. So we're given some x0, and we have some j of t, which is equal to our phi of x of t. This is our final state, so we know where that's going to be. We can calculate what the value function at that time is. But we need to get to j0. How do we get to j0? Well, let's look at this equation and break it down. So we have some value function, and what we can do is this goes from t to t minus 1, but since this is just a sum, what we can do is break out one of these. So now we're left with this equation, where all we've done is extract some L at the current time from the rest of the summation. Well, now what do you notice? This equation should look really familiar. This is the exact same equation we had before, but now for a different time. So what we can do is simplify the equation like this, where this term gets incorporated into j of t plus 1. So now what we have is the value function at the current time and place is equal to the minimum of u times the running cost at the current time and the current control, plus the value function in the future. So now, given some j of t plus 1, we can get j of t. So now we have this equation that moves back in time. So remember, we had some form for j of t, so this allows us to get j of t minus 1, and then we can keep doing this up until we get j0. And once we have j0, we can figure out what the best control is at that time. And remember that this value function j is based on the optimal cost. So we're using a thing called Bellman's principle. And what this allows us to do is essentially say that I'm going to be doing the optimal thing in the future. So I can just parameterize that as j, and then I can solve this equation one step at a time, assuming everything I've done previously is optimal. And when I say previously, remember that we're moving backwards in time with this equation. So let's look at how we do that. So if we plug in t minus 1 to this equation up here, we get out this. So we have j of t minus 1 is equal to j of t, and then the min u of t minus 1, and then we have some running cost based on t minus 1. So then what we can do is, we know what j of t is, so we can add that as well. So j of t is this quadratic function based on this qf, and this is our final cost. And this is a weighting of our final states. Now we're going to resub this in as s, and we're going to do this because it's going to show up later in the equation, and it just makes more sense to start off doing this now. But you can just think of wherever you see an s, you can just replace a qf with right now. So we have j of t, so our value function at the final time, is equal to this equation. And I'm going to drop the subscripts here just so there's not a bunch of t's floating around, but just think of it as the prior time. So we have this, which is just our L of x of u, and then this is, if I were to write this x of t plus 1, which in this case is equal to x of t, in terms of x of t minus 1. X of capital T in terms of x of capital T minus 1 is just equal to the dynamics. So that is what you have here. These are just the dynamics that I've subbed in. So then what I'm going to do is going to multiply these equations out. And remember that AX transpose is equal to X transpose A transpose. You need to both flip the order as well as applying the transpose. This is just a property from linear algebra. So if I multiply those equations out, I still have my cost function here, and then I'm just multiplying out these terms there. So this is great. Calculate the j of t minus 1 given t, and if I were to keep doing this and keep subbing in equations over and over and over again, what I would eventually end up with is I could get all the way back to j of 0. But this equation would get huge, and the algebra would get super complicated and annoying to deal with. So we're just going to leave it like this, and just leave this in this general form for now. So this is great and all, but what I need to do is figure out what my minimum control should be. So now that I have my value function that represents my cost to go in this general form, can I use this to compute the optimal control at the current time? Well, what do we know about the optimal control at the current time? We know that it should minimize this cost function. With this cost function, what I can do is take the derivative and set it equal to 0. If I take my derivative with respect to u and set it equal to 0, I should get some extrema point. And since our cost function is quadratic, finding the minimum of that should give me the optimal control. So that's what we're going to do in the next step. So we have the exact same equation we had before written out, and we're going to take the partial with respect to u. So if we take our partial with respect to u, this term cancels out because there's no u. This term becomes this. This term cancels out because there's no u. This becomes this. And this becomes this term. So now that we have this, we can apply our 1/2, and it's going to cancel out all of our 2's. And what we're left with is this equation here. So if we set this equal to 0 and solve for u, we'll get the minimum u. So that's what we're doing at the bottom here. So I set it equal to 0, and I'm going to move this term over to that side. So I get this. So the next thing I'm going to do is take the transpose of every equation. So something like u transpose r would equal to r transpose u, and so on and so forth. And then the final thing I'm going to do is I'm going to factor out this u. So when I factor out this u, I can then just take the inverse of this entire equation and left multiply it. And when I do that, I will get out this equation here, which I can represent as u star. So our optimal control is equal to negative times this thing we're going to represent as k times our state vector x. And this is our optimal control. So this is a summary of what LQR looks like. So we have some dynamics, which we're going to be linear. We have some running cost that is quadratic. And then we have some phi, or terminal cost, which is also quadratic. We can see that we have this q and this qf. And these are going to be diagonal matrices that users have control over. And essentially what this is saying is how much do you care about reaching that target state? Let's say I have some system that is x, y. So if I care more about reaching the x position over the y position, I can give a higher value in that x position than in that y position, in that diagonal matrix. And what this will give me, I will try to track that position better because I'll get a higher cost for deviating. The same thing can be said about R. If I have a very high cost in R, our controller will be very non-aggressive because it takes a high penalty for applying control. If I have a very low R, our controller will be very aggressive. It won't see a reason to penalize how much control it's giving, so it'll give the highest control to minimize Q as fast as possible. And then we have some value function, which is based on this S of t that we talked about earlier. And S of t at the final time is equal to our terminal cost. And otherwise, we have this equation here. And this is called the Riccati equation. And this is an equation that moves backward in time. So the way we typically think about dynamical systems is that we start at some point here, and we move forward. This is going to be moving forward in time. So we have t plus 1, t plus 2, t plus 3, dot, 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 all the way to t. So what this equation does is it moves backward in time. So we start off here, we have some s of t, then we have some s of t minus 1, s of t minus 2, dot, 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 all the way back to s of t. So when we do LQR, what we need to do is solve this Riccati equation backwards in time. So given some final term that does not depend on x, notice here how it only depends on qf, it does not depend on our final state, we can solve this equation backwards, get some Riccati equation s of t minus 1, and then based on that, the form of k that we have includes s, and what we can do is multiply that forward, multiply that by our x, and we get our optimal control. So in summary, we derived the optimal solution to the linear quadratic controls problem called the linear quadratic regulator. And we can use this problem to solve any problem that fits this form. So problems that I know RoboJackets has used LQR on before or would like to is stuff like wheel speed tracking, or you can do position tracking like RoboCup does. And that's all for this lecture.